Hello, welcome to this presentation. My name is Dimitrii. I am with Intel Labs. And today I will present our work on Redis-SGX, which is a project where we take unmodified vanilla Redis and protect it using Intel SGX. So Intel SGX is a new security extension for modern Intel CPUs. And our team in particular builds software solutions, software infrastructure around Intel SGX. And we are always on the lookout for interesting use cases to test our new hardware techniques, such as Intel SGX. And Redis is a perfect example. Redis is, first of all, is a database where clients connect via a possibly malicious network. So there is an urgent need to protect client data, which are probably sensitive and should be encrypted and integrity protected. Redis is a very mature software solution, and it has a huge user base. So we wanted to show with Intel SGX that you can just take this very mature code base and protect it inside Intel SGX without any modifications. And the third and the most important thing is Redis still lacks basic security guarantees. So with Intel SGX, we can provide them. And there is a mandatory disclaimer on our performance numbers. But let me jump to the motivation for this talk. So let me first discuss the security of Redis in its open source incarnation. So imagine that you're a Redis user. You would clone Redis from a GitHub repository. You will spawn it on your server, and then clients will start connecting to it. And Redis doesn't provide TLS connections to this day, which means that all network communication between the client and the Redis server will be in plain text. And Redis provides this facility to append to log files and create backups on a hard drive. And again, this file system communication is also in plain text. And finally, and something that is frequently overlooked, is that Redis is an in-memory key value store, which means that all key value pairs are stored in your main memory, or DRAM. And importantly, they are unprotected. They are also stored in plain text. So these three states of data are frequently called data in transit for your network communications, data at rest for files stored at your hard drives, and data in use, everything that is stored in main memory. And Redis was developed with this mindset that it doesn't need to do any security simply because all pieces of this infrastructure run inside one enterprise private network, which means that it already has all facilities to protect from remote attackers. The remote attacker would usually have to go through an endpoint, and at this and there, something like a firewall or an intrusion detection system will be installed. So all remote attacks will be thwarted by some other third means. But nowadays, we have this push to outsource all your computations to the public cloud, which means that you as a client will create like a Docker container with Redis inside, push it to your cloud provider, and it will be spawned there on a physical server somewhere in the cloud. Which immediately raises the question, how do the clients actually connect to the Redis database? Because before, everything was in plain text. And obviously, the attacker could simply spy on these network packets, which are sent back and forth in plain text. So data in transit is vulnerable in this case. Another important attack vector is that the attacker can actually just go and steal hard drives or find decommissioned hard drives from the cloud provider. And now she's able to steal information just by scanning through logs and backups of your Redis database. So data at rest is also vulnerable in this case. And this is where solutions from enterprise and cloud providers come. For example, with Redis Enterprise, what actually happens is that there is an additional utility to wrap all network communications with clients transparently in TLS connections, such that your client-server communication is protected end-to-end and encrypted. And similarly, there are solutions to encrypt your files on persistent storage in the cloud. You would either use something like full disk encryption or specialized solutions from, for example, Amazon S3 encrypted storage. And in this case, you're fine. Your remote attacker cannot spy on network connections, cannot scan your hard drive because it's completely encrypted. So everything is fine. Unless you change this threat model slightly and say that, what if the attacker is inside the cloud premises? Well, in this case, the attacker doesn't even need to go and hook into your network interface or into your file system, because she can simply get root access to the physical server which runs your Redis instance and just do a G-core memory dump. And then she can see all key values in plain text, and your private data is stolen. So Redis Enterprise and similar solutions cannot provide protection from this particular use case when your attacker is inside of a cloud. And this can happen if the attacker is a remote attacker, but she finds a vulnerability in your privileged software, like she finds a bug in your Linux operating system, exploits it, and gains root access. This is one scenario. Or simply the attacker can be a system administrator in the cloud that goes rogue and hijacks your physical servers for fun and profit. So this is where the Intel SGX comes into play, and this was the focus of our project. So now with our Redis-SGX solution, we would again take our unmodified vanilla Redis, but now we will run it on a special SGX-enabled Intel CPU, and we put the whole Redis with all its code and data inside a so-called SGX Enclave. And these SGX Enclaves, you can think of them as opaque regions in your main memory, which are transparently encrypted and integrity protected by the hardware itself, which means that everything that you put in your Redis database is automatically encrypted and protected. And of course, we also add the components which add network encryption, so that you have end-to-end TLS encrypted communication between the client and the Redis server. And we also add an additional component to protect all communication with the file system. And I will talk about this more in the next slides. So with our Redis-SGX solutions, we can protect all three states of data, be it data in transit, where we protect connections with TLS, data at rest, when we encrypt all file system I/O, and data in use, for which we use the Intel SGX hardware itself. And in this case, even if you run your Redis instance in a public cloud and you have this insider attacker, she won't be able to steal any data, because all vectors are completely protected. And just to give a bit more context how this actually works, what happens is that we spawn a process in which we create an enclave, and we put the complete Redis code and data inside of this SGX enclave. We add the network component, which we call the network shield, to intercept and automatically encrypt all network I/O. And similarly, we add another software component called file system shield to automatically intercept and encrypt all communication with the file system. And because everything, all the software components run inside of the enclave, and the attacker doesn't have any access to the enclave by the virtue of SGX hardware, there is no way the attacker can spy or steal information or modify your Redis code. And this actually worked very nicely. We put complete Redis 5.0 inside of an enclave, all your basic operations worked. We also tested Lua scripts, like file system persistence, stuff like this. And we also tested the cluster mode. We also tested a distributed version of Redis. And for this, we used a special piece of hardware called the Intel SGX Card, which I will also describe in the following slides, where we were able to spawn 3 Redis instances, connect them in a cluster, and they would communicate via an, again, encrypted Redis cluster bus, and the clients would connect to these 3 instances of Redis running inside of SGX enclaves. And again, the attacker cannot steal or deduce any information. So this was a brief motivation why we actually did this project and what Redis-SGX provides. And the rest of this presentation will be a deep dive into the SGX technology and all the software components that we used. So let's start with Intel SGX itself. But before I explain how the SGX hardware actually works, I will give you a reminder on the kind of low-level mechanisms of how operating systems and processes work. And I will argue that the current protection mechanisms of the current software-hardware stack is insufficient to thwart these insider attacks. So what usually happens is that you would have your Redis process, which you probably spawn in a Docker container on top of your Linux kernel, which probably runs on a virtual machine, which is spawned by a KVM hypervisor, and everything runs on a CPU, of course. And then if an attacker wants to collocate its malicious process and to spy on the Redis process, it's not that simple, right? Because we have all these hardware isolation mechanisms like our memory management units, which restrict accesses to our processes. And we have software isolation mechanisms provided by the Linux kernel or your VM abstraction. So the attacker won't be able to kind of cross these boundaries unless the attacker actually finds unpatched vulnerabilities in your privileged code. And then the attacker simply exploits these vulnerabilities, gains root access to the kernel or to the hypervisor, and then the game is lost. Because the attacker can now do whatever she wants. She can scan the complete memory, or she can do something like a TCP dump to spy on the network packets. She can observe all files in your file system. So in this case, the attacker gains complete access to the Redis process. Or even simpler, the attacker, as I already mentioned, can be an actual system administrator of a public cloud. And then he goes rogue, and he already has all this root access to the privileged software, so he doesn't even need to find vulnerabilities and to craft a malicious process. And this is where Intel SGX comes to rescue. What Intel SGX says is that, what if we don't trust our privileged software at all? What if we take this complete software stack and neglect this? And the way Intel SGX does this, it creates so-called enclaves, completely protected regions of memory, and you can put your applications inside. And in this case, you only trust whatever runs inside of the enclave, and you, of course, trust the Intel CPU that it correctly protects the enclave itself. And in this case, even if the attacker has complete root access to the privileged software, she won't be able to do anything. And just to make it slightly more complex and closer to reality, of course, you cannot spawn a Redis enclave. But what actually happens is that you spawn your normal Redis process. And then in this Redis process, using special hardware instructions, you switch to enclave mode. And then no software can gain access to whatever happens inside of the enclave. And then you exit enclave mode. And what this effectively provides you is reduced trust assumptions. In the classical model, you would spawn your Redis process, and you would trust all the underlying layers of software that they are not vulnerable. And if the attacker finds a vulnerability any vulnerability in any of the privileged software layers, then the Redis process is automatically vulnerable. So the attack surface is your complete software hardware stack. And with Intel SGX model, we throw this classical old model out the window, and we only say that whatever runs inside of the enclave is your attack surface, and of course the CPU, and this small region of DRAM which the enclave creates, where it puts its data. So this is a much smaller attack surface, and part of it is in hardware, which is almost unbreakable. So to reiterate, when you look at Intel SGX from a software perspective, it's a very simple deployment model. You have your normal Redis process, and then you create your enclave as a shared library. And it is actually dynamically linked as a shared library. But whenever you enter this library, you have the all Redis code and Redis data running inside of it. So the Redis process, the wrapper around the enclave, doesn't have any Redis logic in it, but only has this thin shim layers to forward network I/O and file system I/O back and forth from the enclave to the host OS. And Intel SGX provides this guarantee that no other software, including the wrapper Redis process itself, can access inside of the enclave. From a hardware perspective, what happens is that SGX adds some components. But before jumping into that, here is the usual architecture of a normal computer. You would have your CPU package, which contains a couple cores and a cache hierarchy. And you also have your memory models, your unprotected DRAM, which is usually non-encrypted. And whenever your Redis code wants to load some data or store some data to DRAM, it actually goes through a memory controller, the MC component here. And with Intel SGX, it adds an additional logic inside of a memory controller called the Memory Encryption Engine, or ME. And Memory Encryption Engine first, when you create an enclave, it carves out a region of memory for protected enclave data. And this is the region which will be automatically encrypted at all times by the hardware transparently. And whenever your cores execute Redis code inside of the enclave, it doesn't go through the normal memory controller path, but instead it is redirected through the memory encryption engine. And this is how we have this guarantee that all enclave data that leaves the CPU package is encrypted at all times, which means the attacker cannot scan your main memory and reveal secret information. The attacker cannot perform something like a cold boot attack, and the attacker cannot steal any information from the memory bus or perform something like a replay or injection attack. So this is how Intel SGX works at a very low hardware level, but this is just a building block. We still don't know how to put our whole Redis application inside of the enclave. So this is where Graphene-SGX comes into play. What we need to do now is to decide how will we move the complete code of Redis inside of an SGX enclave. So we have our original Redis code, which doesn't have any data in use protection. And one way to do this, the usual way to do this, is to use a framework such as Intel SGX SDK, Software Development Kit. But this requires you to partition your application into two parts: the trusted part, which will run inside of the enclave, and the untrusted part, which usually contains just this I/O logic to communicate with the underlying network and file system. And this is nice. You can completely protect Redis in this case. But it is also very tedious to port. And this is error-prone, because now you have to go and manually separate the logic in two parts. So what we actually want to do is to take our Redis binary, and without any recompilation or any relinking, just take it and throw it inside of our enclave. And this is what the Graphene-SGX framework allows to do. And Graphene-SGX, apart from this, it also has an additional layer of protection called Graphene Library OS, or LibOS. And I will explain on the next slide what it does. And the important part of Graphene-SGX is that you can have all these SGX guarantees without any modifications to your software. So now, one slide on the details of the Graphene-SGX framework. So again, what happens is that you have your Redis executable, you don't modify a line of it, and you have its dependencies. In this case, it's just a shared glibc library. And you want to run it on a host operating system, but inside of an enclave. So Graphene-SGX first provides you the additional abstraction of a library OS. What actually happens is that Redis executable will want to communicate with your host Linux to perform system calls for memory management, for thread management, for network and file system I/O. And the library OS layer, which is just another chunk of software, will try to resolve all system calls, all logic that Redis expects from the underlying Linux system inside of the Graphene-SGX process. And sometimes, of course, library OS cannot resolve system calls, such as network I/O, like read and write and open socket, and file system I/O. They cannot be resolved at the library OS level because it doesn't really have any device drivers. So it actually has to go and communicate with the host operating system. And for this, there is another software layer called the platform adaptation layer, which also adds additional checks and verifications that whatever buffers and values you pass to the host operating system makes sense. And whatever the host operating system returns to you in its buffers is also correct. And after this, the system call can be actually scheduled to be executed on the host operating system. And then Graphene-SGX, of course, provides you its main functionality to put the whole thing inside of an enclave. So Graphene-SGX, under the hood, creates the enclave, populates it with your Redis data, and starts the whole process. And there is another small detail here, is that the platform adaptation layer, whenever it wants to communicate with a host operating system, it has to exit the enclave mode. So this adaptation layer is actually divided into two parts, called the trusted and the untrusted part. And the trusted part will simply exit enclave mode, and the untrusted part will forward the system call from Redis to the host operating system. So this is how Graphene-SGX works. This is all nice. Now our Redis code and our key value pairs are transparently encrypted by the SGX hardware. But this is not enough. We also need two additional components in software called the network and the file system shields. So the problem is that even though we run Redis inside of an enclave and our database is automatically protected, as soon as we want to communicate with the outside world, for example, we want to write a reply to a client request, it will be sent in plain text, because Redis sends everything in plain text, to the host operating system. And while this data is still residing inside of an enclave memory, it is protected. But as soon as it gets out, it is unencrypted and can be intercepted by the attacker. So we have a window of vulnerability here. So what we have to do is to add an additional software component called the network shield, which will intercept all this network I/O and automatically, transparently wrap it inside TLS encrypted connections. And at this point, the attacker cannot observe network I/O, cannot modify it in any way, because the attacker can see only encrypted data outside of the enclave, and the attacker cannot peek inside of an enclave. And the similar thing happens with file system I/O. Again, Redis doesn't do anything special about like writes and reads to underlying files. So everything will happen in plain text. And again, we need another software component which we developed called the file system shield. And again, the file system shield simply intercepts all file system functions and transparently encrypts all your like file blocks and dumps them into the underlying host OS file. And again, the attacker cannot read the encrypted file and cannot pick inside of the enclave, so we are completely protected in this case. So we are almost done with the software infrastructure. The only remaining part is the remote attestation of our Redis enclave, which runs somewhere in the public cloud. So the problem is that the client starts communicating with Redis and wants to start sending its private information to the Redis instance, which is presumably running inside of an enclave. But the client actually has no way of knowing if it's really so. The client actually needs to answer two questions. First, how do I know that the correct Redis code runs inside of the enclave? And second, how do I know that this enclave is the actual genuine enclave running on an actual Intel CPU? Because, so remember that the usual solution for such questions would be PKI, public key infrastructure, where as part of a TLS handshake between the client and the server will send its certificate, TLS certificate, and the client knows the certificate authority. It trusts the authority which issued the certificate to the Redis client. Actually, the certificate authority issues a TLS certificate to the cloud provider, and the cloud provider kind of propagates it through the Redis server back to the client. And the client simply compares that the certificates are correct. But in our case, we cannot really trust the cloud provider, right? Because it is malicious. It has an attacker inside. And the attacker could simply say, I don't want to create an actual SGX enclave into which I will not be able to pick. So I will just emulate it. And my Redis will simply run as a normal plain text process. And it will fool the client to believe that it actually communicates with an actual enclave. And if the client can be fooled, then the attacker can simply perform a memory scan. And she wins again. So what is missing in this picture is something that will tie this enclave and this enclave identity to the CPU which runs this enclave. So what actually happens is that all SGX-enabled Intel CPUs have a private key, which is burnt into its fuses. It is extremely hard to extract, actually impossible to extract, and it is not known to any other party. It is not known even to Intel itself. So with this private key, what the SGX infrastructure can do is to take Redis code during creation of the enclave, measure all code pages in the sense that it will take the hash value over all initial code pages, and sign this measurement of the enclave with a private key of the CPU. And this is something that is called the SGX attestation evidence. And importantly, because the attacker cannot steal the private key of a CPU and cannot forge it, and the attacker doesn't have access to the code running inside of the enclave, the attacker cannot forge the SGX attestation evidence. Which means if our client somehow obtains the public key for this particular CPU from an Intel service and receives this SGX attestation evidence as a part of a TLS handshake, the client can compare the signature and be sure that the client talks to the real Intel CPU. And the client will also compare the measurement, the hash of the code, with the hash that it expects. And thus, it will be sure that it actually talks to the correct Redis instance. So this is how remote attestation works with Intel SGX. We don't rely on the normal PKI infrastructure, but it is something slightly different. And with this, we have the complete software hardware infrastructure to protect our Redis instances. But we also wanted to experiment with Redis in cluster mode to see if it can scale. Cluster mode is just mode when you spawn several Redis instances, connect them into one entity, and then all client requests will be load balanced among several Redis servers. And for this, we use the Intel SGX Card, which was announced a couple of weeks ago at the RSA conference. And this SGX card is a very nice piece of hardware. It's basically a PCI Express card, which you can plug into your normal server rack. And it has free independent SGX-enabled CPUs. So now you will have your server in a public cloud with this Intel SGX card. We spawn free Redis-SGX instances running in free independent SGX enclaves. And then the clients can connect to each of these instances through a host CPU, which simply serves as a kind of bridge network interface. And with this, we can highlight how Redis can scale even when we put it inside of an SGX enclave. And there is a final slide. So up until this point, we didn't change a line of Redis. We just put the normal unmodified Redis executable inside of an enclave, and it works. But we also wanted to go a step further, and we actually looked at the virtual memory feature of Redis, which was introduced several years ago, but then quickly abandoned. But we kind of revived it for our own purposes. So the idea, the motivation for this Redis performance optimization is that we have this protected enclave region of memory, but it is extremely small. In comparison to your normal DRAM, which could be gigabytes and terabytes of data, we only have around 128 megabytes of enclave data in current SGX implementations. In the future, it will be much more. It will be in gigabytes. But for now, we are restricted by this 100 megabyte enclave memory size. And this doesn't mean that you cannot create Redis instances with more than 100 megabytes. It just means that whenever your working set size is larger than this 100 megabytes, then SGX hardware, together with the kernel, will start swapping these enclave pages out to the rest of your DRAM. And this is an extremely slow process. So what we actually ended up doing is we kind of moved up this swapping of enclave pages to the user level. And this is the only change that we did for Redis. So what we initially had is our Redis enclave, which contains all keys values, the whole database inside of the enclave. And what we wanted to have is our Redis enclave with a minimal memory footprint. So we only store the metadata, like the pointers and the expiration times and versions of our key value objects. But all keys and values, all the actual database, is stored in this other chunk of memory, which is unprotected. Importantly, all metadata and all code of Redis is still inside of the enclave and is still automatically protected. But these keys and values, which we now swap out, should be manually encrypted. So we added this logic for manual encryption and swapping. And if you know about virtual memory of Redis, this is exactly the same. We basically copy-pasted a lot of code from there. And it's about 700 lines of code. And for us, for our restricted SGX case, we achieved pretty significant performance improvement of around 20%. The number depends on the exact workload. And this leads me to the end of my presentation. So there is one slide on evaluation and some performance numbers that I want to show you. This is again from the RSA conference. We showed it a couple weeks ago. And what I'm showing here is that we compare the native unprotected Redis on the left-hand side with the SGX protected Redis on the right-hand side. And we deploy it on this SGX card where we have free Redis instances. And we have a client which is connected through the internet backbone to the SGX server. And we achieve almost the same throughput of 95%, which shows that even though we add all these additional layers of security, in certain circumstances, under certain workloads, we have almost the same performance. And this leads me to the end of this talk. I described our Redis-SGX project, where we put unmodified Redis with all its code and data and protect it with an Intel SGX technology, such that all states of data, be it data in transit, data at rest, or data in use, is completely protected against remote and insider attacks. And there is a lot of information on Intel SGX on the official side and around the internet. And Graphene-SGX, the framework that we use to put Redis inside of an enclave, is an open source project, and we actively develop it. And all these scripts that I developed to put Redis inside of an SGX will be open sourced in the near future. And with this, I would like to thank you and take any questions.
So I'm familiar with SGX. I'm actually doing POC right now as we speak, okay? I'm doing it because we deal with encryption and data encryption keys, which obviously need to be protected. I'm not sure I understood the use case in this particular. Open source, everything is available. What do you need to protect? There's no data encryption key. It's just key value database. Are you protecting data with SGX?
Yes.
It's very expensive.
OK. Well, I wouldn't say that it's very expensive. It really depends on your use case. It really depends on the optimizations that you do. And I'm not sure which kind of framework you used, but there are many tricks that you can play to reduce the overhead of SGX and the overall software infrastructure. So for example, with Graphene-SGX, you can have like maximum of 20% overhead for many workloads. It's significant? OK, but well, sure, yeah. I guess it depends on your performance and security requirements.
Question is about you said the performance only about 20% degradation,
if you mean,
or 95? Oh, okay, only 5%.
Yeah, in this particular case, it's 5%.
Is that an indication that the latency increase is about 5% only?
OK, yeah. Here I show the throughput number. Latency increase was about 20%.
20%. Okay. The second part is this card is going to be the single point of failure in the system.
Well,
do
again,
you have redundancy built in?
There is no redundancy in the card. But again, you can actually, it really depends on your deployment, because you can create a cluster with a failover. So you would have a master-slave Redis cluster mode. So you would have, for example, 2 SGX cards, right? One will have 3 master instances of Redis. The other one will have 3 slave instances. And then they know about each other. They communicate with each other. And you can always do a failover from one SGX card to another.
The other thing is denial of service. I mean, somehow people can figure out how to deny the service rendered by this card.
So this SGX card doesn't really, technically, it doesn't provide you any new mode of deploying Redis, right? It's just that instead of 3 independent servers, you would have 3 Redis instances on one server. And then, again, depends on your use case. If you can, if you would have 2 servers with these 2 cards, then you could easily do a failover.
Yeah, I can see that. I mean, from system design point of view, it sounds like this thing is going to be a forklift upgrade, meaning that the hardware and software all needs to be reconfigured and redesigned.
What has
in order to make this server system really highly available?
Well, again, what has to be redesigned is your deployment model. right? You wouldn't, if you need fault tolerance, then you wouldn't put all your Redis instances on one server.
Right.
Yeah, so this would be similar here.
But we also want the security, right?
Sure.
Right. So I mean, this thing. Well, what I meant is this thing will require a new generation of server design, because from the whole system point of view, it's not just adding a PCI card.
Okay, yeah. I agree. I wouldn't say that it requires like a new model, but it just requires some changes to your normal deployment model.
It's a system refresh.
Okay, a system refresh, yes.
Right. What I meant is not a simple thing, but still, I mean, this is a good idea. But again, I mean.
So again, you can under-utilize this SGX card. In this particular case, you could just spawn one Redis instance on one of these 3 CPUs, and the other 2 will do whatever. And then you're back to your normal deployment model where one Redis instance per one server. You could also do that.
We can get offline. Thank you.
Yeah, thanks.
How would you do upgrades on Redis?
So there is no real change to this. Actually, maybe you could expand a bit on this. Do you mean that when we close one Redis instance in the cluster and then spawn another one? Is this what you mean?
No, sorry. So, for example, suppose that in a few months we have a new version of Redis.
Yes.
How would you deploy the newest version of Redis on that card?
Yep. Just like you would do it with normal Redis. So you have your free Redis instances, which run in cluster mode. You can repartition it before we update. You can repartition so that all keys are moved to the 2 instances, such that the first instance is doesn't have any data now. So you can simply close it. You can tear it down, update your Redis, put it inside, and then spawn it again inside Graphene, now with new version. And then you can repartition your key values back using the normal Redis cluster mechanisms. Does this answer your question?
It does answer your question. I'm not clear on all the steps, but it does answer my question. Thanks.
Okay, yeah, we can take it offline.
Okay, thank you. Thanks.
Hi. Thank you for the talk. I had a question about the benchmarks and kind of the setup there, because you compare to 50 KOPS per second, which is fairly low for Redis, right? You can get to like, now I'm writing something with memory, or I'm getting to 200K. So kind of what's the setup to justify like a fair comparison?
Yep, it's a great question, and that's why I have this small remark at the bottom of the slide. So I guess the culprit here, 2 things here. We're testing, this particular case shows 4K values, and I think 64 byte, so 4K byte values and 64 byte keys. So this is already slightly different how people usually benchmark. It also tests uniform distribution of keys. And importantly, it is over 1 gigabit Ethernet cable, because we connect the client via internet.
You talked about how you're reducing the attack surface against the kernel in the hypervisor, but so only the CPU is still vulnerable. Does the SGX architecture do anything to protect the firmware on the hardware level?
The short answer is no. So of course there are rigorous verification procedures at Intel. But there is like no additional logic in this project to protect the CPU somehow. This particular project assumes that the CPU itself is completely correct. I'm sorry? Including the firmware, yes. Yep, thank you.
Thank you.